Hello everyone, welcome back to this week's algebraic graph theory seminar. This week, Sophia is going to tell us about Cayley graphs, association scheme, and state transfer.
Thanks, Tina. And thanks to all the other organizers of this seminar. This talk is going to be based on a paper by Chris Gottsel and myself that we put on arXiv this summer. And the paper is about perfect state transfer on Cayley graphs. But I kind of wanted to talk about, I kind of wanted to emphasize in this talk sort of the tools that we use in the paper rather than the main results, just because I think that's fun sometimes. And basically the tool that I'm going to talk about is association schemes. So I'm going to start this talk with something I've never started a talk before, which is an abstract. So this is what I'm going to do in this talk. Basically, I'm going to have that there are going to be two parts. We're going to talk about association schemes, and then we're going to use association schemes to prove this theorem here. This is just a theorem about Cayley graphs. And it's nice because it seems like a theorem that you can easily prove just using group theory, but that actually doesn't seem to be a good way to do it, but it's easily proved using association schemes. So the theorem says that if G is an abelian group of odd order, then any non-empty Cayley graph for G that has integer eigenvalues will have an odd eigenvalue. So we're going to prove this using association schemes. And then I'm going to talk about the results of the paper, which basically are a characterization of perfect state transfer in graphs that we call two circulants. And I'll explain that a bit later. And our results, so we do use this first theorem to prove our results. And I'm going to try to make that connection very quickly as well if I have time. So this is the abstract of the talk. If you read the abstract that was in the email, that wasn't an abstract for this talk, really. And now, so here's an outline. So we're going to start with Cayley graphs. Basically, we'll just define Cayley graphs and some of their properties, and then we're going to talk about association schemes. I am going to be assuming that many people who are listening have seen association schemes and are familiar with them, but I'm still going to go through preliminaries, maybe just quickly. And then we're going to talk about eigenvalues of association schemes. And then there are two specific types of association schemes that we care about, which are the conjugacy class scheme and then the integral translation scheme. And then at the end of this section, we're going to prove the first theorem. And then the third section is about perfect state transfer. We have the preliminaries and then the other stuff, which is the results of the paper. And in this particular talk, I'm not going to talk about any motivation for studying perfect state transfer, because I feel like I'm always talking about that, and I wanted to do something different this time. And also, I think many people, again, in the audience maybe have heard that before. And if you haven't, then I will just tell you that people are interested in perfect state transfer, and it is fun to study. So let's start with Cayley graphs. So we have a group G, and we take a subset of this group C that does not contain the identity, and we're going to assume that this subset is inverse closed. And then the Cayley graph that we denote by K of G comma C has the group elements as its vertices, and the elements G and H are adjacent if HG inverse is in the set C. And we are going to call the set C the connection set of the graph. So we have a group and a subset, and those two define a graph for us. Okay, and so some examples, we have the cycles, for example. They're Cayley graphs for the cyclic groups, where we take the connection set just to be plus minus 1. We have the hypercubes that are Cayley graphs for Z2 to the D, where the connection set is the standard basis. And then we have the complete graphs, and actually Kn is a Cayley graph of any group of order n, where the connection set is the whole group except for the identity. Okay. And then, so we say that a Cayley graph is normal if the connection set is closed under conjugation. So the connection set is a union of conjugacy classes of the group. And then we say that a Cayley graph for an abelian group is called a translation graph. And you notice maybe that a translation graph is always a normal Cayley graph, because in an abelian group, the conjugacy classes are singletons. And actually, in this talk, we are going to be focusing on normal Cayley graphs and translation graphs. And in general, being a normal Cayley graph is actually a really nice property for what we are studying here. It makes everything a lot easier. Okay, so in particular, we have cube-like graphs, which are Cayley graphs of Z2 to the D. So for example, the hypercubes are cube-like graphs. And then we have circulants, which are Cayley graphs of the cyclic groups. And so in particular, the cycles are circulants. And actually, we're going to be talking more about circulants later. And that was it for the Cayley graphs. Okay, I should also say, especially maybe during this next section, because it's going to be maybe long and a bit technical, if you have any questions, please just shout them out or ask them in the chat. I don't think I can see the chat currently. Maybe I should change that. Okay, now I have the chat open. Anyway, yeah, so feel free to ask questions. So we're going to start with preliminaries of association schemes. An association scheme is a set of n by n matrices. We're going to call the set script A, and the matrices are going to be called A0 to AD. They are 0-1 matrices, and they satisfy the following. A0 is the identity matrix. If we take the sum of all these matrices, we get the all ones matrix, which we are going to call J. The set script A is closed under taking transpose. All the matrices in the set commute with each other. And then finally, the product ARAS lies in the span of this set for all R and S. So AR times AS is in the vector space that's spanned by script A. And this actually means that this span is not just a vector space, it's an algebra. We denote it by C of A, and we call it the Bose-Mesner algebra of the scheme. Any 0-1 matrix in this algebra is what we call a Schur idempotent. This is because we talk about the Schur product as the entry-wise product of the matrices, and these are all 0-1 matrices, so they are idempotent under the Schur product. And And then in particular, these matrices that we defined the scheme with, AR, are the minimal sure idempotents in the Bose-Meissner algebra. And any sure idempotent is actually going to be a sum of some of those minimal sure idempotents. Okay. And now, if we have our scheme A and we then take another scheme B with matrices B0 to BK, where each of those is a sure idempotent in the Bose-Meissner algebra of A, then this is going to be a subscheme of A. So this means that every minimal sure idempotent in our new scheme is a sum of some of the minimal sure idempotents of our first scheme. Okay, and then the Bose-Meissner algebra for B is going to be a sub-algebra of the Bose-Meissner algebra of A, which is not very surprising. Okay, and then so we have this whole algebra here. We're mainly interested in the 0-1 matrices, in these sure idempotents in the algebra. And actually, because these are 0-1 matrices, we can think of them as the adjacency matrices of a graph or a directed graph. And we talk about those graphs as the graphs in the scheme. This is really nice because we have this this algebra, and now we have these graphs, and we like graphs, so that's nice. Okay. Now we want to define eigenvalues for an association scheme. And to do that, we're first gonna define another basis, so an association scheme always has this 0-1 basis. So the script A is a basis for the algebra. But we actually have another basis of matrix idempotents. We're going to call that basis E, and its matrices are E0 to ED. And they satisfy the following. E0 is going to be 1 over the all ones matrix. Sorry, 1 over n times the all ones matrix. The sum of all the ER is the identity matrix. Script E is closed under taking transpose. These matrices are pairwise orthogonal. And then the sure product, which this is how we denote the sure product, which is the entry-wise product of the matrices. The sure product of any two of these lies in the Bose-Meissner algebra. And then these matrices E0 to ED are going to be called the minimal matrix idempotents of our Bose-Meissner algebra. Okay. Tina, you look confused.
I'm not confused.
Okay.
Thank
You
you.
just look it. Okay. All right. So now we have two bases of a vector space, which means that we can write any element of this vector space as a linear combination of the elements in the bases. So in particular, we take a matrix AR, and we can write it as a linear combination of the ERs because they form a basis. I'm going to do that in this way, and we get these scalars here, which are the coefficients of this linear combination. And similarly, we can write every ER as a linear combination of the ARs. We get these other scalars here, QR of S. We put in 1 over n in this one just because why not? And so now if we look closely at these equations here, we can actually see that if we multiply AR and ES, we get PR of S times ES. So here we can replace this AR by this sum here. The matrices are all orthogonal, so they disappear except for one of them. And so this means that the column vectors of ES are eigenvectors for AR, and this is the corresponding eigenvalue. And so these scalars here are all eigenvalues of the matrix AR. And we call so we're going to call these scalars PR of S, the eigenvalues of the scheme. And so S goes from 0 to D, and R goes from 0 to D as well. So those are the eigenvalues of our association scheme. And now we're going to put these eigenvalues in a matrix. We define P and Q by letting P SR be PR of S, and then Q we define similarly. And P is called the matrix of eigenvalues of the scheme, and Q is the matrix of dual eigenvalues of the scheme. Okay, and then we actually have, and again, we can just see this by staring at these two equations we had before, that P times Q is equal to N times the identity matrix. And that's important. So now we have this scheme, and we have some eigenvalues of the scheme, but what we actually really care about are the graphs in our scheme. That's how we're gonna sort of that's what we're gonna use all these tools for, is to study graphs. So if we have a graph in the scheme, what can we say about the eigenvalues of the graph using the eigenvalues of the scheme? Well, so if we have a graph in the scheme, then its adjacency matrix is a sure idempotent in the Bose-Meissner algebra. We can write it as a sum of some of the minimal sure idempotents. So we just have some subset R of 0 to D, such that if we sum over this subset, these AR, we get our matrix A. And then if we just take the indicator vector for R, then the eigenvalues of our matrix A are going to be the entries of P times X. So they're actually just going to be sums of some eigenvalues of the scheme. So this is how we can get the eigenvalues of a graph in our scheme from the eigenvalues of the scheme. I'm going to ask for questions now so far. Is everything clear? Okay. Okay, then next we're going to talk about the conjugacy class scheme. So we've defined these association schemes, and what we are going to use them for is to study Cayley graphs. So now we're going to sort of make that connection. We take a group G of order n, and we look at its conjugacy classes. We call them C0 to CD, where the convention is that C0 is going to be the identity element. That's always a conjugacy class on its own. And we define these matrices A0 to AD. They're going to be indexed by the group elements. And the GH entry of AR is going to be 1 if HG inverse is in the conjugacy class CR, and 0 otherwise. And you might already see that AR is going to be the adjacency matrix of the Cayley graph for G that has CR as its connection set. Okay, and now no surprises here. This is actually an association scheme, and we call it the conjugacy class scheme of G. And so the graphs in this scheme are going to be normal Cayley graphs for G. And also any normal Cayley graph of G is a graph in this conjugacy class scheme. So this is we have an alternative definition of a normal Cayley graph. Actually, it's a graph that lives in a conjugacy class scheme. There is a comment in the chat, which is a good comment, that so the matrix idempotents of an association schemes, the ERs, they are orthogonal projections onto the eigenspaces of the ARs. Yeah, anyway. Okay, so in particular, we're going to look at abelian groups, and for pretty much for the rest of this talk, we're going to focus on abelian groups. And so we have this conjugacy class scheme, and then what happens to that when our group is abelian? Well, the conjugacy classes are just singletons in an abelian group, and so this scheme consists of permutation matrices, which doesn't seem like that doesn't seem like a very interesting scheme. But it is a very important one still. So the conjugacy class scheme of an abelian group G is called the abelian group scheme of G. And then even though that one is maybe not the most interesting, we can look at any subscheme of this scheme, and we're going to call that a translation scheme. And now a graph in a translation scheme is a translation graph of G, and any translation graph of G lies in a translation scheme of G. Okay, so again, we have another definition of what a translation graph is. Okay, so now we're going to talk about duality a little bit. And duality is something that I think maybe arose from translation schemes, but I'm not sure. But translation schemes, they happen to be either what we call formally self-dual, or they have another scheme that is dual to that scheme. And this is not something that happens in general with association schemes. It happens in all translation schemes, however. And that's, I think that the dual schemes is something that hasn't been studied that much. And it seems like it could be useful for some things. So if we have an association scheme A with matrix of eigenvalues P and matrix of dual eigenvalues Q, then we say that this scheme is formally self-dual if the complex conjugate of Q is equal to P. And here is just a basic theorem, which I think we can just call folklore. The abelian group scheme for an arbitrary abelian group is formally self-dual. And that's easy to prove if we just know that the matrix of eigenvalues of the abelian group scheme is actually the character table of the group. And then, so remember that we always have that P times Q is equal to N times the identity. And now we can just use basic character theory to finish the proof. Okay. So for every group, we have this conjugacy class scheme. For every abelian group, we have a translation scheme, or we have the abelian group scheme and its subschemes, which are translation scheme. But we want to actually look at a particular subscheme, which is the integral translation scheme. And we define it as follows. So we're going to take the group and we're going to define an equivalence relation. So we say that two elements, G and H, in our group are power equivalent if they generate the same cyclic subgroup. This is an equivalence relation on our group, and we let D0 to DK be the equivalence classes. And we're going to call them power classes. And now, quite similarly as before, we define these matrices A0 to AK by letting the GH entry of AR be 1 if HG inverse is an element of this power class DR, and 0 otherwise. And this is indeed a scheme, and we call it the integral translation scheme. And again, I want to point out that the matrix AR is the adjacency matrix of the Cayley graph of G that has DR as its connection set. Okay, so this is called the integral translation scheme. And why would it be called that? I'm sure you're asking yourself. So we say that a graph is integral if all of its eigenvalues are integers. And now we have this theorem here that a translation graph of G is integral if and only if it lies in the integral translation scheme of G. Okay, so this this power equivalence is actually a sort of a characterization of integrality in Cayley graphs of abelian groups, this is quite a useful and quite a powerful tool, actually. And then we can also show that the integral translation scheme of an arbitrary abelian group is formally self-dual. Okay, that's not as trivial to show that as it is for the abelian group scheme. But it is true. And now we can prove this theorem here, that if G is an abelian group of odd order n, then any non-empty integral Cayley graph for G has an odd eigenvalue. Okay, so if we have such a graph, we're going to call it X, then it lies in the integral translation scheme of G. The integral translation scheme is self-dual So so the complex conjugate of the matrix Q is equal to P, and now because P times Q, or P times Q is equal to N times the identity, then we also have here that P bar times P is N times the identity. And also we know that the determinant of P is real. And then we just have this equation here. We can actually, the punchline is that the determinant of P is an odd number. Okay. So the determinant of P is an odd number, which means that the matrix P is invertible modulo 2. And now if we remember how we get the eigenvalues of the graph from the eigenvalues of the scheme, we have some 0, 1 vector X, and our eigenvalues are going to be the entries of Px. But now if we assume that all the eigenvalues are even, then so all the entries of this Px are even, then Px is equal to 0 modulo 2. But P is invertible modulo 2. And so X must be the 0 vector. And if X is a 0 vector, then this big X is the empty graph. And that's the proof. It's actually quite simple once you have all the tools, and pretty short. And now I'm pretty sure, Chris and I talked about this a while ago, and I think we came to the conclusion that this probably also holds for normal Cayley graphs, and not just Cayley graphs of abelian groups. But then I started trying to write it down again, and I just didn't quite get there. But I'm pretty sure this is true. Okay, so this is what I wanted to say about association schemes. Are there any questions now?
May I ask a question?
Sure.
So, so when you very quickly said that the group scheme is self-dual, you have these arbitrary orderings on the elements and the relations and the eigenspaces, and I mean, it can't be self-dual for every possible permutation, right? So you didn't mention that you have to choose an isomorphism between the group and its dual group of characters. Was there a reason why you didn't want to talk about that, or do you have a shortcut that avoids choosing an isomorphism?
No, that's, I mean, well, do you mean the abelian group scheme?
Yeah, in the abelian group scheme,
Yeah.
you said that
Yeah.
obviously P is equal to Q conjugate, but that of course depends on orderings.
Yes. No, that's true. We can always order the character table so that it's symmetric. Wait, is that? Yeah. It actually, so in the proof of the integral translation scheme being self-dual, that's in that proof, actually this ordering becomes kind of messy. Like you have to really think about how to choose that ordering, which is why that proof is not that easy. But with the abelian group scheme is that, so we know that we can do this with a character table from character theory, I guess. So is that a satisfactory answer?
Thank you.
Okay. But yeah, no, I mean, it's yes, you're right. So okay, any other questions? Okay, so let's quickly talk about perfect state transfer. Like I said before, I'm not going to give a motivation or anything here. I'm going to go very quickly through the preliminaries. So we have a graph X with adjacency matrix A, and we define this matrix U of T for a real number T by e to the power of ITA. And so if we take this collection of matrices U of T for all real numbers T, this gives us a quantum walk on the graph X. And U of T is going to be called the transition matrix of the walk at time T. And then we say that there is perfect state transfer from vertex X to vertex Y in our graph if the XY entry of U of T has absolute value 1. So then we have perfect state transfer from X to Y at time T. Okay. And here's just a small theorem that we're gonna use, is that a regular graph that admits perfect state transfer has to have integer eigenvalues. So in particular, Cayley graph that admits perfect state transfer is integral. Okay, and just to see a few examples of perfect state transfer, we have perfect state transfer in K2. We have it in P3. We have perfect state transfer in the hypercubes. A lot of other cube-like graphs, some circulants, and a lot of, or some other Cayley graphs as well. I'm pretty sure that we do have perfect state transfer in some non-Cayley graphs that are also not P3, but I couldn't give you an example. Probably someone else here can. But the point is kind of that a lot of our examples of perfect state transfer actually come from Cayley graphs. At least a lot of the examples that we have currently, and sort of the point here is that most graphs do not admit PST. But we like graphs that admit PST, so we wanna find them. So now we're coming to the sort of the results in our paper. Remember that a circulant is a Cayley graph of the cyclic group Zn. Previously, we had a characterization of perfect state transfer in circulants. So Milan Basic proved a characterization in 2011. And what we did in this paper is that we generalized this characterization to what we call two circulants. And so a two circulant is a Cayley graph of an abelian group that has a cyclic Sylow-2 subgroup. Okay, what does it mean that a group is abelian and has a cyclic Sylow-2 subgroup? Well, it just means that we can write it on this form. We can write it as a direct product of a cyclic group of order a power of 2 and an abelian group that has odd order. So we have a group G. We say, oh, this is an abelian group with a cyclic Sylow-2 subgroup, and it has order 2 to the d times m, where m is an odd number. That means that it's a direct product of z2 to the d and some h, which is abelian and has odd order. Okay. So here, in the case where H is a cyclic group, we have a circulant, because then G is a cyclic group as well. But this is a generalization in the sense that H does not have to be cyclic, it just has to be abelian. Okay, so And so for the rest of this talk, we are going to write our group G in this form. And so we have this group Z2 to the D, and we have this group H. Okay, and now we, so it does seem in the study of perfect state transfer in Cayley graphs, this cyclic, or sorry, this Silo2 subgroup does seem to play an important role. And so we have, it is important here that we have a unique element of order 2, and we have a unique pair of elements of order 4. So if D is at least 1, which if it's not, we have a group of odd order, and then we have no perfect state transfer. So we don't have to worry about that. If D is at least 1, then we have a unique element of order 2 in our group G. We call this element A, and this is going to be important. And then if D is at least 2, then we also have a unique pair of inverse elements of order 4, and we're going to call those B and minus B. So now we have, because of a group, we're going to think of it as additive. Okay, we have our group, and we have the unique element of order 2, which is called A, the unique pair of inverse elements of order 4, which are called B and minus B. Okay, so here's just an example of a graph, which is a 2-circulant. It's a Cayley graph of this group here. And it is not isomorphic to a circulant. And it does have perfect state transfer. Okay, so now we know that if we want our 2-circulant to have perfect state transfer, then it's going to have integer eigenvalues. And when does a translation graph have integer eigenvalues? It's exactly when it lies in the integral translation scheme. And so we're going to have the connection set be closed under this power equivalence relation that we defined earlier. So we can just assume that our connection set is power closed, because otherwise it does not have perfect state transfer. So we take a power closed subset of G, which means that it is closed under this power equivalence relation. And now we're going to partition our connection set in the following way. We let CK be the set of elements in C that have order 2 to the K times an odd number. So we're going to look at an element of C, we're going to look at its order, and we kind of just care about the power of 2 in this order, and not the sort of odd part. Okay, so in particular, C0 is going to be the subset of elements of C that have odd order. Okay, and now I've written out this a little table here. So we have our group, which is the direct product of these two groups, and C0 is a set of elements of odd order, which means that it's a subset of H. So H is the subgroup of G, which contains all the elements of odd order. Okay, so our C0 is going to be contained in H. Okay, then what about C1? We can actually, so C1 is the set of elements in C that are that have order 2 times an odd number. So if A is in our set, connection set, then it's going to be in C1. And actually, we can write the C1 as a direct product of the element A, and then some set, which we're now going to call C1 star, which is contained in H. So all the elements here are actually going to be A times some element of odd order. And similarly, we can do this with C2, except now on this side, we have plus minus B. So all the elements in C2 can be written as a product of B or minus B and some element of odd order. And we're going to write C2 as this Cartesian product of this set plus minus B and a set that we now call C2 star, which is contained in H. So we have C0, C1, C2. What happens with the rest of the sets? It actually doesn't matter. They're not going to play a role in whether our graph has perfect state transfer or not. As long as we've chosen the whole set to be power closed, which means that each of these is actually power closed. But aside from that fact, it doesn't matter what's happening there. And so we look at these three sets here. Actually, we see that C0 cannot contain 0 because then 0 is contained in C, which we don't want in general for a Cayley graph. But 0 could be contained, in either of those. Aside from that fact, just to spoil what's on the next slide, the punchline here is basically that to get PST, we need all of those sets basically to be the same set. So here's the theorem. We have a Cayley graph, which is a two-circulant of a group G with respect to the set C. It admits perfect state transfer if and only if the following hold. C is power closed. Either A is in C or B, but not both. And these three sets here are all the same. So here we've just ignored the part where we could have 0 in one of those sets. If we take that out, then they're all the same set. And just to tie this very quickly back to our the first part of this talk, we're going to just go through a very rough sketch of the proof. So of one part of this proof, which is that if we assume that X admits perfect state transfer, then this part 3 holds. That was actually the part that I proved the last. It was a tricky one. So this is the idea of the proof, that if we have PST, then 3 holds. We define this set S to be the union of these two sets, where we basically take the difference of C0 and C1 star minus 0, and then the difference the other way around. And so what we're going to do here is that we want to show that S is empty, which is going to mean that C0 is equal to this set here, which is what we're trying to show. So S is a subset of H, the subgroup of our group which contains all the elements of odd order. And so now we define the Cayley graph of H with respect to S. This is an integral Cayley graph of odd order. And we know that such a Cayley graph has to have an odd eigenvalue. But we can actually show that if the graph has perfect state transfer, then Y has to have only even eigenvalues. And so therefore S must be empty and these two sets must be the same. And we just do the exact same thing with S2 star. So that's the proof. And now I just want to sort of, this is the end of the talk, and I just want to throw out there that I have been thinking about whether we can maybe generalize these things to normal Cayley graphs. We actually do know that we can generalize some of the things that we've done to normal Cayley graphs. Could we possibly generalize all of this to normal Cayley graphs? That would be really nice. Thank you.
Thank you for the talk. So is there any question for Sophia?
This isn't much of a question, but I'll just ask, for the bridges and mana paper that you referred to, is that this rational G matrices with rational eigenvalues?
Yep. Wait, it's either that one or the other one.
There's another one too? Okay.
There is another one, and I always confuse them. But yeah, I think it's that one. It's not, I wouldn't say it was obvious how you get that particular theorem from that paper. Because it's, well, their language is just a little bit different to maybe what we are used to. And but I sort of go through that pretty thoroughly in my thesis.
Nice. Thanks.
So any other question for Sophia? Okay, so I was actually wondering, like, you say you can generalize it to some of the normal Cayley graphs, or like some of the property can be generalized to normal Cayley graphs?
So yeah, they could. So I'm hoping that some of these things that we have done, and maybe even this characterization of the perfect state transfer, that could be generalized to normal Cayley graphs, like all normal Cayley graphs.
So some of them you already being able to generate.
No. So what we have done is that we have proved this other. I think we have proved this theorem for normal Cayley graphs.
Okay.
And we use this theorem in more parts of the paper to get the perfect state, to get the characterization, and in particular, I think so. Sort of an important part here is that when perfect state transfer happens in a two circulant, then it has to happen at time pi on 2. Like, it can't happen faster.
Okay.
Which is kind of the problem in cube-like graphs a little bit, because it seems very difficult to characterize perfect state transfer in cube-like graphs because it can happen arbitrarily fast. But in the circulants, it happens at time pi on 2 or not at all. So I think to prove that, we also use this theorem here. And even just proving that holds for normal Cayley graphs with the cyclic Sylla-2 subgroup, that would be nice.
Okay, thank you.